My name's Darren Holmes, and today we're going to be using the EMAC Primer Trainer to look at lesson number 9, Binary Coded Decimal 16-Bit Addition. Under New Instructions, we have the DAA command, opcode 27, and this changes the value in the A register to 2 binary coded decimal digits. And this is going to take a bit of an explanation, so we'll cover that momentarily. The second new instruction is the NOP, or No Op instruction. Its opcode is 00. And it says this instruction does nothing but take up 1 byte in a program and no flags are affected. It also wastes some time. So on page 747 of the 5th edition of your textbook, we have the DAA command. It's called Decimal Adjust Accumulator. You'll see it's 1 byte, 1 machine cycle, and takes 4 T-states, and its hex code is 27. Under description, it says the contents of the accumulator are changed from binary value to 2 4-bit binary coded decimal BCD digits. It says this is the only instruction that uses the auxiliary flag internally to perform the binary to BCD conversion. And it says the procedure for the conversion is described below. Now the flags, they're all altered to reflect the result of the operation. And it says the instruction DAA converts the binary contents of the accumulator as follows. So looking at the example in the textbook, we're going to add the decimal number 12, because it's in BCD, to the accumulator, which contains 39, which is also a BCD number. So you can see 39 is 0011, 1001. It's just the binary equivalent of those two numbers. So 12 is 0001, 0010. Now when we add the BCD numbers together, 9 plus 2 is equal to 1, carry the 1, so 1 plus 3 plus 1 is 5. So the BCD answer is 51. However, doing this with the microprocessor, we can see 0 plus 1 is 1, 1 plus 0 is 1, 0 plus 0 is 0, and 0 plus 1 is 1. So 1, 0, 1, 1 is greater than 9. It's actually B in hexadecimal. So we're going to have to correct for this, and that's going to generate an auxiliary carry. So looking at the high order bits, we can see 1 plus 1 is 0, carry the 1. 1 plus 1 is 0, carry the 1, and then 1 plus 0 is 1, and then 0 plus 0 is 0. So on the high order bits, we can see we have the number 4, but on the low order bits, we can see we have the number B, and that's a hexadecimal number. So you can see here in your textbook, it says the binary sum is 4B in hexadecimal. The value of the low order, 4 bits, is larger than 9, so we add 6 to the low order 4 bits. So 6 is 00000110. So we're going to add that to the 4B. So 0 plus 1 is 1. 1 plus 1 is 0. Carry the 1. So it looks like they put the carry bit down here. So 1 plus the carry bit is 0. Carry the 1. 1 plus the carry bit is 0. Carry the 1. So that's the auxiliary carry they're showing right there. So you can see our low order bits are now 1, which is what we expected when we do BCD math. So now we have the auxiliary carry plus the 0 gives us 1, and then 0 plus 0 gives us 0, and then 0 plus 1 gives us 1, and then 0 plus 0 gives us 0. So now we have the number 5, 1, which is the addition for BCD numbers. So by adding 6 to anything that's greater than 9, we come up with the correct BCD addition. So your textbook has another example. I suggest you read over it and try to understand it as best as you can. So on page 759 of your textbook, we have the NOP instruction, which is no operation. You'll see that it is 1 byte, 1 machine cycle. It takes 4 T-states and its hex code is 00. Under description, it says no operation is performed. The instruction is fetched and decoded, however no operation is executed, and no flags are affected. Under comments, you can see this instruction is used to fill in time delays or to delete and insert instructions while troubleshooting. So you can see it does take 4 T-states even though it does nothing. So I thought at this point it would be interesting to access the Primer Trainer Self-Instruction Manual. This is Appendix C, the Instruction Set Encyclopedia. It's available both in Manual Revision 2.5 and Revision 3. So on this page, labeled 8085A CPU Instructions in Operation Code Sequence, I thought it would be interesting to step back and just take a look at all the commands we already know how to use. Now there's 256 commands in total, all the way from 00 to FF. Now a lot of them we haven't used, but a lot of them we have used. So you can see some of these I've highlighted all the way across because those are the ones we have used, but these are all the move commands. So I think once you've used a few move commands, you should be able to understand the rest of them. So I'm going to go in and show you a few of these commands now. So you can see the no operation command is actually code 00. Then we have the INXB command, which we know increments is the BC register pair. The move immediate command, which moves data into the B register. The double add command, the move immediate command. The move commands, now we've used the move A into B, but I'm sure we could just as easily understand how to move C into B. Now you'll notice there's a command here to move B into B. So I just want to refer you back to page 757 of your textbook, where we do have the move command, where it says copy from source to destination. You can see there is a move from B into B, and the opcode is 40. There's also a C into C, a D into D, E into E, and so forth. You'll notice no flags are affected. No matter what you do, it's 1 byte, 1 machine cycle, and 4 T-states. So moving B into the B has the same effect as a no operation command. It just wastes 4 T-states. You'll notice there's a whole bunch of add commands. We've used the add C and the add E, but I'm sure you can just as easily use the add B or the add D command. Looking towards the last column, we can see we have C3, which is the jump command to an address, and D3, which is the out command. So you can see all these opcodes are listed numerically. So we still have a few more to cover, but we've covered probably over half of them already. So if you've forgotten what BCD numbers are all about, I want to refer you back to Sham's Outlines, Digital Principles, 3rd edition that we used in our Digital Systems course. And in Chapter 2, they talk about binary codes. And in Section 2-2 of your textbook, they talk about weighted binary codes. And in Figure 2-1, they have a table showing the 8421 BCD code, where they take the decimal numbers 0 through 9, and convert them to their binary equivalents, all the way from 0000 to 1001, representing 9. And then you might want to review Figure 2-2, where they show you a few examples of converting decimal to BCD numbers. So looking down here, it says decimal numbers can be stored in binary form as binary coded decimal numbers. It says each decimal digit takes 4 bits, just as a hex number do, but in BCD, digits A through F are not valid numbers. Right, it says, for example, the hex number 9999 is 9999 in BCD format. It says the DAA instruction was provided so it would be possible to perform binary coded decimal math using the ordinary hex addition instructions. So according to its definition, DAA will give the following results following a hex addition instruction. And they give you 3 examples here. One where they're just adding 6 to the low order nibble. Remember, nibble's 4 bits. In the next example, they're adding 6 to both the low and the high order nibble. And in the last example, they're just adding 6 to the high order nibble and showing you what the results will be. It says, note that the DAA can only give 2 decimal digits and the carry flag as a result. In these examples, the carry flag represents the 100th digit. So here we have 142. That is a decimal number because we've adjusted it after the hexadecimal math. So it has to do the hexadecimal math first, and then the DAA command will actually convert it back to binary coded decimal. So looking at the code for today's lesson, you can see it's broken down into 2 parts. We're going to add the low order bytes first. So we're going to move C into A, then we're going to add E, and we're going to set the carry flag if A is less than E. We're going to do the decimal adjust accumulator, and then we're going to move A back into C. So that's A plus E gets moved back into C. Then we're going to add the high order bytes and the carry from the DAA. Right? So the previous decimal adjust will either set or reset the carry flags. So we have to remember to add that back in. So basically, for the high order, we're going to move B into A. So A is a copy of B. And then we're going to add with carry. Right? A is going to be equal to A plus D plus the carry flag. Then we're going to decimal adjust that number. And then we're going to store A into B. So BC will now have our answer. And then we're going to do the restart 7 to stop the program. So we're to enter the program into memory and then press reset. And then we're going to load BC with 1934 and DE with 1879. So they've broken it down into steps for us, and after you've loaded the program and the BC and D register pairs with the data, we're going to single step to FF03 and examine the A register. It will be AD in hex, and it says since both the upper 4-bit and lower 4-bit binary digits of the A register are greater than 9, then 66 will be added to it in the DAA instruction that follows. So each line of the code is broken down, and we're just going to single step from now on and see what shows up in our accumulators and registers. So I've gone ahead and loaded the program into memory. You don't need to watch me do that every lesson. The BC register pair is being loaded with 1934. The DE register pair is being loaded with 1879. So we're at a single step until we get to FF03, and then we're to examine the A register. So function AF register. It says the result will be AD in hex. Now it says since both the upper 4 and lower 4 binary digits of the A register are greater than 9, then 66 will be added to it in the DAA instruction that follows. Now I just want you to note that some of the flag bits did get set in here. Okay, the first digit being 8 indicates that's 1000, so the sign bit has been set. And the 2 in the second digit indicates that that is 0010. So that's the V flag register being set, and that's supposed to be undefined. So I just want to refer you back to the documentation of Lesson 4, 8-bit addition, where I introduced the flag register, and we had the most significant bit was sign 0, the undefined or K flag, the auxiliary carry, the undefined or 0 flag, the parity bit, the undefined or V flag, and the carry flag. And you'll remember I introduced you to Ken Sharif's blog, where he showed us the circuit for the K and V flags. And in the documentation it says the V flag is simply the exclusive OR of the carry into the top bit and the carry out of the top bit. It says this is the standard formula for computing overflow for signed addition and subtraction. And they gave us a little schematic here of carry 6 and carry 7 going into an exclusive OR and coming out as the V flag bit. So when you're working with microprocessors, you do have to understand what's going on internally. So I've redrawn the flag register just as a memory aid, and also the hex numbers above 9. Sometimes we have trouble remembering them, so it doesn't hurt to write them on the side of your page. Now BC is loaded with 1934 and DE is loaded with 1879. And at FF01 we load C, which is 34, into A, so that's 0011, 0100. Then at FF02 we're going to add E to the accumulator, which is 79. So you have to remember the bit pattern for that is 0111, 1001. So then we're going to add it together. So you have to add the bits together to find out what flags get set. So 1 plus 0 is 1, 0 plus 0 is 0, 0 plus 1 is 1, and then 1 plus 0 is 1. So the auxiliary carry bit did not get set. Then for the next part, 1 plus 1 is 0, carry the 1. So then 1 plus 1 plus the carry is 1, carry another 1. Then 1 plus 0 plus 1 ends up being 0, carry the 1, and then 1 plus 0 plus 0 is 1. So that's how we end up with AD. Remember 1010, and you can look back up here for 1010 is A. Now we have to look at this and say, okay, the flag bits got set as 82. So this bit here for the 8, 1000, that's the sign bit. So the sign bit just comes from the last bit of our answer, the high order bit of our answer. Now the 2 is the V flag. So how did that get set? So you notice the carry bit is actually 0. But the carry into the last bit that we added together was 1. So this is 0, 1, 2, 3, 4, 5, 6. So the result of the 6th bit being added together generated a carry into the 7th bit. So what we have here is 0, 1 going through an exclusive OR, generating a V flag bit equal to 1. So that's where the 2 came from. Then at FF03, we're doing the DAA command, which adds 6, 6 to our answer. So 6 is 0, 1, 1, 0, 0, 1, 1, 0. So when we add these together, 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 1 is 0, carry the 1, and now we have 1 plus 1 is 0, and there's our auxiliary carry bit being set. So then 1 plus 0 is equal to 1, and 1 plus 1 is 0, carry the 1, 1 plus 1 is 0, carry the 1, 1 plus 1 is 0, carry the 1, so there's our final carry bit being set. So our answer ends up with a flag being set as 1, 1, so the first one is the auxiliary carry, the second one is our final carry. So I'll leave you to carry on doing the rest of the calculations to prove that the program does work. So at FF03, I'm going to do a step. And this did the DAA instruction. So let's take a look at the A register, function A. And we can now see that the A register contains 1, 3. The flag register, you'll notice, is 1, 1. So 0, 0, 0, 1 indicates that the auxiliary carry bit is set, and then 0, 0, 0, 1 indicates that the carry flag is set. So it says now to single step to FF07. So step, 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 and we're to examine the A register. So function AF, it says it will be 3, 2. And we can see that the flag register contains a 1 in the most significant 4 bits. So that is 0, 0, 0, 1. So that indicates that the auxiliary carry bit is set. 0 in the second 4 bits indicates that the carry flag was cleared. So press enter to get out of the register display. So at FF07 we're supposed to single step the DAA instruction, and we can examine the A register. So function A, and we can see that 6 was added to it. So we're now at 38 instead of 3, 2. Press enter. So now we're going to single step again, and it says the A register will be copied to the B register. So we're going to verify that the B register, so function BC, is 3813, which is our answer. So it is the sum of the decimal numbers 1934 and 1879. So I know you're probably asking, why would we want to add BCD numbers together? Remember, if we were writing a program for somebody, they would be using standard decimal numbers to enter data. So when they enter data in standard decimal numbers and we try and add them together, we have to remember that we're adding in hex, and then we have to convert back to BCD when we display the answer for the person using our program. So in the last part of the procedure, it says now replace the DAA instructions at FF03 and FF07 with FF00. So at FF03, I'm going to replace the 27 DAA instruction with 00 and press enter, and then go back to make sure that you did replace it. And the next location is FF07, so we're going to put in 00, enter, and then go back to make sure that we did replace it. Then we'll hit the reset button. And now we're to load D, E, and BC with the same values as before. So, function BC gets 1, 9, 3, 4, enter. And function DE has 1, 8, 7, 9, enter. So now I'm just going to press function run, and it says this time the BC and DE registers will be added as if they were hex numbers, and the result will be 31AD. So function BC, the result is 31AD. I've now updated the simulator to version 1.3, and for the upgrades I just want to refer you back to Ken Sharif's blog on the circuit for the K and V flags. So in version 1.3 of my simulator, I've implemented the V flag, and the V flag is simply the exclusive OR operation of the carry going into the most significant bit and the carry coming out of the most significant bit. So I've run a few example programs with this and it seems to be working correctly. So I'm now going to release version 1.3 of my simulator with the implementation of the V flag. I've also partially implemented the K flag. Now the K flag actually performs 3 different functions. Okay, so in the first function of the K flag, it's the overflow or underflow for the INX or DEX instruction. So you can see that comes in from here and goes up and makes up part of the K flag. But we have 2 other inputs going to make up the K flag. So it says in the information above that the next function of the K flag is reading from the data bus for the POP PSW instruction, which I have not implemented at this time. And then it says the final function of the K flag is the result of a sign comparison, which I have not implemented at this time. So the only thing I've implemented at this time is the V flag and 1 function for the K flag for the INX and DEX instruction, and I've checked these with some sample code and find that they both seem to be working at this time. So when I was going through lesson 9 on the primer trainer, I was a little bit surprised to see that the V flag bit had been set. So I've come along and I've upgraded the simulator, so we're now on version 1.3, and you can see in version 1.3 the flag V is the carry from bit 6 exclusive ORed with the carry out from bit 7. So that has now been implemented and tested. The K flag, I was trying to implement that at the same time, and I've only got as far as the INX overflow and the DCX underflow. So I have some more updates to do as far as the K flag is concerned. So I've gone ahead and loaded the program into the simulator. So the first thing that I need to do is load the BC register, so function and BC, and I'm going to load that with 1, 9, 3, 4, and press enter. And now I'm going to load the DE register, so function DE, and I want to load that with 1, 8, 7, 9, and press enter. So under my procedure here, I'm to single step to FF03. So step, step, and now it says to examine the A register. So function AF. And it says it will be AD. So there's our AD. And it says since both the upper 4 and lower 4 binary bits of the A register are greater than 9, then 66 will be added to it in the DAA instruction that follows. So keep in mind, the flag register was set to 8.2. So if I go up to View and say Register Contents, you can see right here that 8 is the sign bit being set, because we have AD in the A register and the most significant bit is a 1, so that sets the sign bit. And we can see down here that the V flag has been set. So we can press enter to get out of the AF register pair display, and we should still be at FF03. So we're going to single step the DAA instruction, so step, and it says to examine the A register, so function AF, and it says that you will see 66 is being added to it, which set the carry flag and made the A register 13. So once again, I'm going to go to View, Register Contents, and I'm looking for the carry flag, and it was set to 1. Press enter to bring me back to FF04. It says single step to FF07. So step, step, step. And we're to examine the A register, function AF, and it says it will be 3.2. Now it says here the auxiliary carry flag will be 1 and the carry flag will be 0. So I'm going to go to View, check my register contents, and we can see here the auxiliary carry was set to 1 and the carry flag was reset to 0. So it says in the instruction that follows, it will add 6 to the A register. So we'll press enter. And at FF07, we'll do a single step for the DAA instruction. And we're going to examine the AF register pair. And you can see that 6 was added to it. 3.2 plus 6 equals 3.8. So everything seems to be working correctly. Press enter. At FF08, it says single step, and the A register will be copied to the B register. So single step, and we can now check the BC register pair and see that the answer is 3813. And it says here to verify that the BC register is indeed 3813, which is the sum of the decimal numbers 1934 and 1879. So now we're to press the reset button, and we're going to change the instruction at FF03, so increment, increment. So we're going to change it to 00, which is the no op or do nothing command. And we want to increment to FF07 and change that 27 to a 00. Press enter. Now we're going to go back and reset. So we're FF01. We now have to load, and we're going to load the registers as we did before. So the BC register is 1934. Enter. And the DE register is 1879. Enter. And it says to run the program. So we press function run. And we're going to check our answer. So we're going to look at the BC register, function BC. And it says the registers will be added as if they were hex numbers, and the result will be 31AD. So our simulator seems to be working. This concludes lesson number 9, binary coded decimal 16-bit addition. In lesson number 10, we're going to be looking at multiplication using the Primer Trainer. So don't forget to subscribe so you don't miss this lesson.